Charge is a property of matter determined by the amount of protons and electrons there are. Electrons are negatively charged, while protons are positively charged. Per mass, electron has a stronger charge because the mass of an electron is a lot smaller than that of a proton. An object gets charged through the manipulation of electrons. When electrons are removed, it becomes positive, while electrons are added, it becomes negative. Right now, in this Van der Graaf machine, the orb is negatively charged because the moving carpet belt is causing the orb to gain a lot more electrons. As I move my hands closer, the transfer of charge from the orb to my hand is simply the transfer of electrons. The bolts that you might be able to see are streams of electrons that are being transferred into my body.
Today we will be discussing Coulomb's law. Coulomb's law is the equation that says force is equal to K times Q1 times Q2 all over R squared. K would be Coulomb's constant, which is a very large number. The Q1 would be the charge of that object, Q2 would be the charge of this object, and the radius of the R squared would be the radius of both of these squared. Now if we look here, we can see that the charge is projecting this thing, this styrofoam, apart. That is a force. It is Coulomb's constant times the charge of this times the charge of that over the R squared.
The electric field is equal to the force per coulombs. Negative charges attract the electric field and positive charges repel the electric field. Here's an example of that. In the Van der Graaf belt generator, the electric field travels towards the center. Because the electric field repels away from positive charges and is attracted to negative charges, when two positive charges are placed together and act on a point, they create a net electric field that goes through the middle. Similarly, a negative charge and a positive charge acting on a point create a different electric field that goes upwards.
We've seen before, an electric field is force per charge. Therefore, an electric field will cause a force on an object. And by knowing that, we can see that an object will move once placed inside an electric field. Intuition tells us, by just looking at magnets, that opposites would attract. So if we have a negative charge here and another negative charge here, we'd see that they repel. Likewise, if we had a positive charge and a negative charge, they would attract. Now, as it is, we have two negative charges. So let's see how it... As we see, because there's two negative charges, the force will be exerted this way, pushing the two charges away. As we see here, a charge inside of an electric field will be if it's negative and a negative, away. If it's a positive and a negative, towards. Opposites attract and likes repel. Right now, we'll be talking about electric potential. This combines two topics that we had previously covered. First is potential. For instance, this is gravitational potential, the amount of potential energy that gravity has on us. For instance, if I drop it, then what will happen is the potential energy, because of the gravity, will turn into kinetic energy. And likewise, we have a similar phenomenon in electricity. See, because as we discussed earlier, there's an electric field going out. This charge, because they're both negative, will push each other out. So if we were to... If we were to push these two close together, there will be electric potential. However, if we were to move them far apart, there's electric potential. But the moment we push it away, the force will push it away. This is difference in potential. See, as it goes back and forth, that's because there's potential. When we move it close together and push it away. That's enough.
This is a circuit. Electricity flows from the batteries through the wires, producing a current, and thus making the light bulb light up. This is a resistor. It slows down the current, thereby reducing the electron flow. However, if we were to take out the resistor, the light is a lot brighter. This is a capacitor. It stores charge. Right now, it is not allowing the light bulb to to light up. If, however, we take it off of the capacitor, the light bulb then lights up. This is a series circuit. All the components are in the same loop. The current is the same, but the voltage is lower. This is a parallel circuit. The components are in different loops. The voltage is the same, but the current is different. Magnetic force can cause magnets to repel or attract each other. When two opposite poles are put together, one magnet goes farther away. But if two similar poles are attached together, they can attract, causing them to stick together. A magnetic field is the area around a magnet in which the magnetic force acts. A magnetic field can also be created using an electromagnet. Here we will demonstrate what a magnet field looks like by placing a magnet underneath some iron filings. As you can see, something will happen. See, there we go. We have a nice vision of what it might look like.
There's a pole on this end and a pole on this end. The poles seem to attract in loops, as you can see here, and then they go out that way.
Okay, let me close in. See that? Notice how the filings are spread apart from the center of the magnet underneath the paper towel.
Okay. We can explain. When the magnets go through the copper wire, the magnetic field is changed. The copper wire attempts to neutralize this change by creating an electric current going in the counterclockwise direction. As you can see, there's a change in magnetic flux. There's a change in electric current right now due to the change in magnetic flux.